Morning. Today I want to discuss a continuation. We're going to continue our discussion on Chapter 19. So to summarize where we've been so far, in the beginning of the chapter, we introduced this idea of thermodynamics, right, as the study of spontaneous reactions, right? This is the reactions that will proceed without any outside help, right? Now, one of the main things that we're trying to do here is figure out some way that we can determine whether a reaction is going to occur spontaneously. So we're trying to develop what's called this chemical potential, right? This would be analogous to what we think of as mechanical potential energy, right? Which predicts, right, that things will fall when we drop them, etc., right? So we want to come up with something analogous for a chemical reaction. Now, in the beginning part of the chapter, we addressed, enthalpy, delta H, as a potential candidate for this chemical potential. But we determined that enthalpy alone cannot be this chemical potential because endothermic reactions such as melting can also be spontaneous, right? So if it was enthalpy alone, right, we would predict that exothermic would be spontaneous, endothermic would not be, because exothermic reactions lower the enthalpy, right? They lower this potential. So enthalpy is not our chemical potential. So then we introduced another thermodynamic function, entropy, right? S, right? Which is a measure of disorder or energy dispersal. If we think of it sort of in a general way, we had a specific definition, right, that describes, the number of energetically equivalent states, but typically we just think about it as increasing or decreasing the disorder of a system or the energy dispersal of a system. Along with this, we introduced the second law of thermodynamics, right, which really establishes that this entropy idea is a criteria for a reaction to be spontaneous, right? And so the second law, to remind you, says that the entropy, or the delta S, of the universe must increase for a process to be spontaneous. So in other words, if a process occurs, it must increase the entropy of the universe to be spontaneous. So this is the same, so that, the idea that the second law says that spontaneous reactions will increase the energy dispersal in the universe, right? Or nature's sort of natural tendency is to increase the energy dispersal, right? We gave the example of your coffee in the morning, right, spontaneously cooling down, right? Because that energy is being spontaneously dispersed out of the coffee into the surrounding areas, right? Now, we also, during this time, introduced the entropy of the universe, right, as the sum of the entropy change of the system plus the entropy change of the surroundings, right? Falling back on the old thermodynamic idea we introduced back in Chapter 7 of dividing the universe into the system and the surroundings. But we also looked at the idea that entropy alone can't explain spontaneity, right? We can't just look at entropy by itself, because we saw that some processes that actually decrease the entropy, right, or that have a decrease in entropy, are also spontaneous, right, such as condensation and freezing, right? These processes have a decrease in entropy, right? They're becoming more ordered, but they still occur spontaneously under the right conditions. So, how is this possible? Well, the explanation, if you remember, that we gave, or that we looked at, is that these processes give off energy into the surroundings and therefore they increase the entropy of the surroundings. So in other words, these processes had to be exothermic in order to be spontaneous, because remember, we have to increase the entropy of the universe. So if a system had a decrease in entropy, then that means the surroundings had to have a bigger increase in entropy so that the universe would have an overall increase in entropy. So we got into this idea that the system itself can have a lowering of entropy as long as it's exothermic and the surroundings have an increase in entropy that is greater than the decrease of the system, so that we meet the second law that the entropy of the universe increase. So we don't violate the second law, right? Spontaneous reactions always increase the entropy of the universe. So we also established, right, the relationship between the entropy of the surroundings as an equation and how it is directly related to the enthalpy or the negative enthalpy of the system, right? So in other words, right, we have an exothermic reaction, right? We're going to end up with an increase in entropy of the surroundings. And it was inversely related to the temperature, right? That the increase in entropy of the surroundings is more if the temperature of the surroundings is lower, and it's less if it's higher for the same amount of energy that's given off. So we established this relationship between the entropy change of the surroundings, the enthalpy of the system, and the inverse relationship with the temperature of the surroundings. So in other words, an exothermic reaction here, remember exothermic reactions would have a negative delta H, so a negative would give a positive change in the entropy of the surroundings. And that change is going to be more significant if the surroundings are at lower temperature. So the bottom line here is that neither enthalpy by itself or entropy by itself can be described as the chemical potential that we want to finally get to. Right? So what we're going to do in today's class or today's lesson is discuss another thermodynamic function known as Gibbs free energy, or delta G. Now, we can see here on the slide, and I'll focus right here, is that formally we can define this or describe this thermodynamic function as the maximum amount of energy that can be released to the surroundings by a system at a constant temperature and pressure, or at a given temperature and pressure, right? We're not changing them. Now, we're going to come back to that a little bit later, and for now, we're going to look at how we come up with an equation for delta G, or how we came up with this idea of delta G. At this point, we want to look at coming up with an equation for delta G, right? What is this thermodynamic function? How did we come up with the equation that we use? So if we look at two equations that we have right now, we have the entropy change of the surroundings is equal to the negative delta H of the system divided by T, and we also know that the entropy change of the universe is equal to the entropy change of the system plus the entropy change of the surroundings. So first thing is we're going to do a little bit of a substitution here, and we're going to rewrite this equation here as delta S of the universe equals delta S of the system plus negative delta H of the system over T. So we have that. We're going to then multiply through by T, or negative T actually. And so we're going to get negative T delta S of the universe equals negative T delta S of the system plus delta H of the system. And we'll clean this up a little bit here and just rewrite it as delta T of the universe equals delta H of the system minus T delta S of the system. So now we have this relationship between T delta S of the surroundings, or the universe, and the entropy of the system and the enthalpy of the system. Right? So we're describing the entropy change of the universe in terms of the system characteristics, the enthalpy of the system and the entropy of the system. Now, the right-hand side of this equation, right, is what we define as the thermodynamic quantity as Gibbs free energy. Now, so if we rewrite this equation, the right-hand side express it as delta G, Gibbs free energy. So we can say that Gibbs free energy is equal to delta H minus T delta S of the system. Now, so this is one way. This becomes our fundamental equation for Gibbs free energy, right? The Gibbs free energy change of the system equals the enthalpy change of the system minus T delta S of the system. Now, if this is equal to delta G of the system, what that also means is that the delta G of the system is equal to minus T delta S of the universe. And why this relationship is important is that we've already established, right, that the delta S of the universe is a criterion for spontaneity, right? Second law says that for a process to be spontaneous, the delta S of the universe must be positive. So if the delta S is related to Gibbs free energy, that means that Gibbs free energy, or delta G, must also be a criterion for spontaneity. So now we have our chemical potential, right? Delta G, this Gibbs free energy, is that chemical potential that we've been looking for, the way that we can describe the spontaneity of a process. And we can do it based on the enthalpy change of the system and the entropy change of the system given the temperature, given the specific temperature. Now, what it also tells us here is that if delta S, right, a positive delta S of the universe equals spontaneous, according to this relationship, a negative delta G equals spontaneity. So delta G is our chemical potential, and we need a process to have a negative change in free energy in order to be spontaneous. So to summarize here, that Gibbs free energy, or delta G, is proportional to the negative delta S of the universe, right? As we see here. And that means that a negative change in Gibbs free energy, or a decrease in potential, right? Just like we see with mechanical potential energy, right? We want processes that are spontaneous will tend to decrease, right? So it makes sense. A decrease in the Gibbs free energy, or negative delta G, corresponds to a spontaneous process, and an increase in Gibbs free energy, or a positive delta G, would correspond to a non-spontaneous process. And it's related, of course, as we see in this equation, to the enthalpy change of the system and the entropy change of the system at a given temperature. Now, the next thing we're going to try to do is we're going to look now at this equation, right? This is our go-to equation, right, to figure out delta G, to try to determine whether a given process is spontaneous. We want to look at how different values of delta H and delta S can help us predict spontaneity without even actually having any numbers in hand. So now let's look at how we can take the values of delta H and delta S for a given process and try to determine the spontaneity, right? And this is all going to go back to using our equation, our delta G of the system equals delta H of the system minus T delta S of the system. So if we use this equation as our guide, there are four possibilities if we just consider the sign of delta H and delta S. So if we take the first example here, right here. So if we have a negative delta H, right, or in other words, exothermic, right? So remember that a negative delta H equals exothermic, and a positive delta H equals endothermic. And if we think about it, a negative delta H would favor spontaneity, right? An exothermic reaction is favoring spontaneity because we're releasing energy, right? We're dispersing energy, right? Now, the reminder that a positive delta S, right, increases disorder or energy dispersal, or disorder, and a negative delta S decreases these things. And again, it is the positive delta S that's going to favor a spontaneous process, right? The natural tendency, right, is to increase the energy dispersal, right? That's what nature strives for. So as we're thinking about this, right, a negative delta H will favor spontaneity, a positive delta S will favor spontaneity. So in our first example, where we have both a negative delta H and a positive delta S, right, a reaction will always be spontaneous, right? So mathematically, we can look at this, right? If delta H is negative and delta S is positive, then we will always have a negative plus a negative, and so we will always going to be having a negative answer, right? So for any value of t you plug in here, you're always going to end up with a negative answer. If you look at our second criteria, that is our second example, if we have a positive delta H, so an endothermic process, and a decrease in entropy, so a process that becomes more ordered, right? Under those scenarios, right, a reaction will never be spontaneous at any temperature, right? Because, right, we're not only seeing absorption of energy, right, concentration of energy, we're lowering the energy dispersal. So that type of reaction will never be spontaneous, and we could try it and see that no matter what temperature value we plug in, the delta G value will always be positive. So those two are sort of the extreme cases, right? Either always spontaneous because both favor spontaneity, or never spontaneous because neither of them favor spontaneity. The ones that are a little trickier, that ones we have to really think about and do calculations for, are if we have one of the criteria that favors spontaneity but the other one doesn't. So these are kind of like some of the examples we looked at earlier where we had an endothermic process, right? You know, like freezing, melting, but it was still could be spontaneous, and vice versa, right? We could have a process like freezing that that decreases disorder, but is still spontaneous. So let's look at a couple examples. So let's say we have an exothermic reaction, but it has a decrease in entropy. So this would be, again, like freezing. It would be one of the examples. So if we look at the numbers, this type of reaction is going to tend to be spontaneous as we lower the temperature. Right? So if we think about what that's doing, right, if I lower the temperature, it's, in a sense, lowering the importance of the entropy value, right? So it's lowering this term in the equation. And so as we decrease this, so if we think about it, if this value is negative, right, and delta S is also negative, right? So we have a negative minus a negative, or a negative plus positive, right? As long as this number stays low, then the delta H factor can still win out. As T becomes larger and larger, this term becomes bigger and bigger, and at some point, this quote plus a positive term, the positive part of this will become bigger and will become larger than the delta H term, and will flip this answer to positive or non-spontaneous. Right? So this kind of scenario is going to tend to be spontaneous at relatively lower temperatures. Now, of course, exactly what these temperatures are is going to depend on the process, and we would have to try it, right? We can do trial and error here, depending on the values of delta H and delta S, what temperature value is going to cause that flip to occur. Now, one thing we'll look about later when we go to solve problems is that one way that we can sort of establish that is to see when delta G equals 0, right? When we get to a point where delta G of the system equals 0, that's the flip point, right? So that's one way that we can establish at what temperature that change in spontaneity occurs. So you can keep that in mind when we actually go to solve problems. So now let's look at the last criterion, the last example, which is if they're both positive. So in this case, right, we have an endothermic process, right, with a positive delta H. And we have an increase in entropy, right? So we have a positive delta S. So in this scenario, it's actually the entropy term that we want to maximize, right? Because this is favoring spontaneity, right? So we want to maximize this term and keep this term, less important. So how do we do that? Well, we raise the temperature, right? So this type of reaction is going to tend to be spontaneous at relatively higher temperatures, because at lower temperatures, right, we have a positive minus a positive, or if you want to call it a positive plus a negative. So we want this negative term to be bigger. So as T is lower, then if this term is more important, then delta G will be positive and non-spontaneous. But eventually, as temperature gets higher, this term becomes bigger than this. And so when we do a positive plus a negative, the negative term becomes bigger, making delta G negative, and the reaction becomes spontaneous. So these kinds of processes, for example, vaporization, become more spontaneous at relatively higher temperatures. And again, that exact temperature is going to depend on the process, and we can determine, again, when that flip occurs if we set the system equal to 0 and see what temperature that occurs at. Okay. So that describes sort of the scenarios, the four possible scenarios we can have in terms of the signs of delta H and delta S. And so a lot of times we can just look at the values and without actually even doing a calculation determine whether it's going to be spontaneous or not, and then we can perform the calculation to figure out what the actual delta G value is. And other times we have to figure out, we need to plug it in to see whether it's going to be spontaneous, because the signs alone won't directly give us that answer. We need to know if we've passed that flip point. Okay, so now that we've looked at sort of this part of the equation, we're going to summarize what we've been doing and with this sort of introduction to Gibbs free energy. So I want to conclude this section by just summarizing some of the stuff that we've talked about with Gibbs free energy. So again, we'll come back to this sort of specific definition a little bit later on, but what we want to understand now is that Gibbs free energy is often referred to as our chemical potential, right? It is our predictor of spontaneity that we will use, right? So it's something we can actually calculate, unlike the entropy change of the universe, which is a much sort of trickier idea to sort of compromise. So Gibbs free energy gives us that measure of spontaneity that we can determine based on only properties of the system, right? The enthalpy of the system and the entropy of the system at a given temperature that we're working at. And so delta G is our determiner of spontaneity, and more specifically, right, a negative delta G, right, is what our criterion for a spontaneous process. It must have a decrease in potential energy, because just like our mechanical systems that we're familiar with, where nature tends to, our mechanical systems will tend to move toward lower potential energy, right? Something will drop if you let go of it, right? Falling to lower potential energy. Chemical systems will tend toward lower chemical potential, right? So if we move from our reactants to our products, right, in a chemical reaction, we want that potential energy, that delta G, that change in free energy, to decrease, right? So if we look at this little graph, right, we can sort of see that if you're on one side or the other, right, that we're going to move toward that lower potential energy, right? So the Gibbs free energy will determine that direction of spontaneous change. So going from here to here or here to here, right? Those are both directions of spontaneous change. They lower the Gibbs free energy. Right? So a system is going to move to minimize or to move toward lower free energy. So that's going to put a wrap on what we're going to talk about today. Next time, we'll go back and talk a little bit more about entropy and talk about how we calculate entropy for a given reaction, right? How we calculate that change in entropy.